Tonight the journey moves toward one of the most famous limits in all of science. The speed of light appears everywhere in modern physics. It shapes space-time energy and the structure of the universe itself. For more than a century, scientists have searched for ways to push beyond familiar boundaries, yet one barrier remains untouched. Why can light travel so fast while every spacecraft, every particle with mass, and every human-made machine falls short? As this story unfolds, the physics behind that cosmic speed limit begins to emerge. The answer is not a matter of engineering. It is not a problem waiting for a future invention. It is woven into the laws that govern reality. Before settling in, please take a moment to like this video, subscribe to Cosmic Bedtime Stories, and leave a comment sharing where in the world this journey is being heard from tonight. Now, as the stars drift across the darkness and the universe reveals its deepest rules, the story begins. The observable universe scale forms the outermost context for understanding motion distance and the limits of speed. At this scale, matter is distributed across vast regions of space, filled with galaxies, clusters of galaxies, and enormous voids where almost no visible matter exists. Light from the most distant observable sources has travelled for billions of years before reaching present-day detectors, revealing an image of the universe that belongs to an earlier time. This delay in light travel establishes a fundamental boundary for observation, where distance is inseparable from time, and every region seen is also a record of the past. Within this largest framework, motion is not simply movement through space, but is influenced by the expansion of space itself. Galaxies appear to drift away from each other, not only because of a local motion, but because the fabric of space between them stretches over time. This expansion is uniform on the larger scales, meaning that every distant region participates in the same general separation trend. As distances grow larger, the effect becomes stronger, and beyond a certain range, regions recede in a way that cannot be overcome by any internal motion within those regions. At this scale, the concept of speed becomes dependent on the geometry of space rather than only the velocity of objects. Light travels at a constant speed relative to local space, yet space itself can expand in such a way that distant regions separate faster than light can cross the distance between them. This does not represent motion through space exceeding a limit, but rather the stretching of space itself altering the separation rate. The observable result is that some regions of the universe move beyond the reach of signals emitted from others, not because light slows, but because the distance grows too quickly for any signal to bridge. The structure of the universe at this level is not uniform in density. Galaxies gather into clusters connected by filaments of matter, while vast empty regions dominate the overall volume. These structures form through gravity acting over long periods, slowly pulling matter together while expansion continues to increase the separation between unbound regions. The interplay between gravitational attraction and cosmic expansion defines the large-scale architecture of everything that can be observed. In this environment, the idea of traveling across the entire observable universe becomes physically constrained not by engineering limits alone, but by the structure of space-time itself. Even if an object could move extremely close to the highest possible speed allowed for matter, the expansion of space over intergalactic distances would continue to increase the gap ahead of it. The further it travels, the more it encounters regions where separation grows faster than progress can be made through local motion. The observable universe is also defined by a horizon, a boundary beyond which no information has had time to reach the present location since the beginning of expansion. This horizon is not a physical wall, but a limit created by the finite speed at which light and causal effects propagate. Every region inside this boundary is connected through a chain of light signals that have travelled across time while regions beyond remain unobserved, not because they do not exist, but because their light has not yet arrived. Time itself plays a central role in shaping this scale. The universe evolves as expansion continues, meaning that the distance between 2 points today is not the same as it was in the past or will be in the future. This changing separation means that motion through space is always embedded within a dynamic background. Any attempt to describe movement at this scale must account for the fact that the medium through which motion occurs is itself changing continuously. At the largest observable distances, energy from distant sources is stretched as space expands, causing light to shift toward longer wavelengths. This effect reduces the energy carried by each photon while preserving the fundamental speed at which it travels locally. The transformation of light over cosmic distances provides evidence of expansion and reinforces the idea that distance and time are deeply connected in shaping what can be observed. Gravitational structures also influence how matter behaves within this expanding framework. Massive clusters bend the paths of light and affect the motion of surrounding galaxies, creating regions where local dynamics differ from the general expansion. However, even these gravitationally bound systems exist within a larger environment that continues to stretch. This dual behavior creates a layered structure where local stability coexists with global separation. The observable universe therefore represents not only a region of space, but a limit defined by the age of the universe and the propagation of information. Every point within it is connected through signals that have taken finite time to arrive, and every boundary reflects the balance between expansion gravity and the speed at which interactions can travel. Within this balance, the ultimate limit on motion emerges naturally, as no object carrying mass can fully escape the structure defined by space-time itself. As this outermost layer establishes the stage, it becomes clear that any discussion of reaching extreme speeds must begin with the scale of the universe itself, where even the simplest notion of travel is shaped by expansion, horizon limits, and the finite transmission of light across immense distances. Expanding space itself forms the next layer inward from the observable cosmic scale, focusing on how the structure of space-time changes the meaning of motion across vast distances. In this region, space is not a static backdrop, but an evolving medium that increases in scale over time. The expansion is not centered on a single point, but occurs everywhere at once, so that every sufficiently distant region appears to drift away from every other region as the overall distances grow. This expansion affects how motion is interpreted across long spans of space. Objects such as galaxies may have only small movements relative to their local surroundings, yet the space between them increases steadily. This creates a distinction between movement through space and the stretching of space itself. Local motion follows physical laws determined by gravity and inertia, while large-scale separation follows the metric expansion of the universe, which alters distances without requiring objects to actively travel through intervening space. At moderate distances, gravitational attraction can overcome this expansion. Galaxies within clusters remain bound together because their mutual gravity holds them in stable orbits and long-term structures. Within these regions, space still expands, but the effect is not strong enough to disrupt the internal structure. Motion inside these systems follows familiar rules, where velocities are measured relative to local reference frames that remain stable over long periods of time. Beyond these bound systems, expansion dominates. Distant galaxies appear to recede faster as their separation increases, not because they accelerate through space in the usual sense, but because more space is continuously created between them. This leads to a situation where the rate of separation grows, with distance creating a horizon-like effect on large scales. Beyond a certain range, regions move away so quickly that signals emitted today will never reach them. The concept of speed becomes more complex in this environment. Locally, nothing breaks the fundamental limit on motion through space, yet globally, separation can increase in ways that appear to exceed simple velocity constraints. This is resolved by understanding that the speed limit applies to motion within spacetime, while expansion changes the structure of spacetime itself. Light still travels at a constant speed relative to nearby space, but the space it travels through stretches, increasing the distance it must cover. Time also plays a critical role in this expanding environment. As the universe evolves, the rate of expansion itself changes, influenced by the energy content of space and the distribution of matter. In earlier epochs, gravity slowed the expansion, while in later epochs the expansion becomes increasingly dominant over large scales. This shifting balance determines how quickly distant regions move beyond causal contact. Within this expanding framework, light emitted from distant sources is stretched as it travels, increasing its wavelength and reducing its energy. This stretching reflects the growth of space over time and provides a measurable record of expansion history. The longer the light travels, the more pronounced this effect becomes, eventually shifting visible light into wavelengths that are no longer detectable by human vision. Despite this large-scale separation, local regions remain governed by stable physical laws. At smaller scales, atoms, planets, and galaxies retain their structure, because the forces holding them together are far stronger than the effect of expansion. The expansion of space does not pull apart these systems, because their internal binding forces dominate over the weak stretching of space-time on small scales. However, the existence of expansion introduces a fundamental boundary for travel and communication across the universe. Even if an object could move at extremely high speed relative to its surroundings, it would still face regions where the space ahead expands faster than it can traverse. This means that certain destinations become permanently unreachable, not due to energy limitations alone, but because the structure of space-time continuously increases the separation. This layer of understanding shows that motion is not only about how fast an object moves, but also about how the space around it evolves. The expansion of the universe introduces a dynamic background where distance is not fixed, and where the possibility of reaching far regions depends not only on speed, but also on the changing geometry of space itself. As this expanding structure becomes clearer, it establishes a deeper constraint on motion, setting the stage for understanding how gravitationally bound systems behave within an ever-stretching cosmic environment. Galaxies and local groups form a gravitationally bound layer within the expanding universe, where the influence of expansion is present, but does not dominate internal motion. In this region, matter is held together by gravity, creating stable systems such as galaxies, galaxy clusters, and smaller groupings that resist the large-scale separations seen between unbound regions. The Milky Way sits within such a structure, part of a local group of galaxies that move together through space under shared gravitational influence. Within these bound systems, motion follows a different character compared with the cosmic expansion outside them. Stars orbit the centers of galaxies, driven by gravitational attraction toward dense central regions dominated by large accumulations of mass. These motions are stable over long periods, forming predictable orbital patterns that persist across millions to billions of years. Gas clouds drift through spiral arms, sometimes collapsing under gravity, to form new stars, while remnants of older stars scatter heavy elements back into interstellar space. Although space continues to expand everywhere, the effect within these systems is effectively negligible on everyday scales. The gravitational forces holding galaxies together are strong enough to maintain their structure against the weak influence of cosmic expansion. As a result, galaxies behave as coherent systems, and distances between stars within them remain relatively stable over time. Motion here is governed primarily by local gravitational dynamics rather than the stretching of space-time. Within galaxy clusters, the same principle applies but on a larger scale. Multiple galaxies orbit a shared center of mass, sometimes interacting through slow gravitational encounters. These interactions can distort shapes, trigger bursts of star formation, or even merge entire galaxies into larger structures. Despite these dramatic events, the cluster itself remains bound, resisting the overall expansion of the universe due to its internal gravitational strength. However, even within these bound systems, motion has limits shaped by relativity. As objects move faster within a gravitational field, their energy increases and additional energy input produces diminishing returns in speed. This is because the relationship between energy and velocity becomes non-linear, at high speeds gradually requiring more energy for smaller increases in motion. This effect becomes important when considering any attempt to approach extreme velocities within galaxies. The structure of galaxies also introduces regions of varying density. Near galactic centers, gravitational fields become stronger due to the presence of dense stellar populations, and in many cases supermassive black holes. In these regions, space-time is more strongly curved, and motion is influenced not only by Newtonian gravity, but also by relativistic effects. Orbits can become faster and more compact, and light itself can be bent around massive objects, altering the paths of observation. Farther from galactic centers, the gravitational field weakens and stars move in broader, slower orbits. These outer regions are often filled with sparse gas and isolated stellar systems where gravitational interactions are less frequent. Yet even here, motion remains bounded within the overall structure of the galaxy, which itself moves through space as part of a larger group. The local group of galaxies, including the Milky Way and Andromeda, is gravitationally bound and is expected to remain so over long timescales. These galaxies move toward each other under mutual attraction, even while the broader universe continues to expand around them. This creates a layered structure where local collapse and global expansion coexist, each dominating at different scales. Within this context, the limits of speed begin to emerge more clearly. Even in environments where space is not expanding significantly, objects cannot accelerate indefinitely. As velocity increases, relativistic effects begin to alter the relationship between energy and motion, making it progressively harder to approach the speed of light. These constraints exist independently of cosmic expansion, arising from the deeper structure of space-time itself. Galaxies therefore represent a transition zone between the largest cosmic scales and the more localized environments where relativistic physics becomes the dominant factor in limiting motion. While expansion defines the boundaries of the universe on the larger scales, gravity defines structure within galaxies, and both together create the stage on which all motion ultimately unfolds. As the view moves inward from these vast structures, the focus shifts toward environments where motion becomes increasingly governed by local forces and energetic constraints, setting the foundation for understanding speed limits within stellar systems. Stellar neighborhood dynamics describe the motion of matter within a galaxy at the scale of individual stars and surrounding gas, where gravity from local masses becomes the dominant influence on movement. In this region, space is filled with stars separated by vast distances compared with planetary systems, yet still close enough for their mutual gravity to shape long-term orbital behavior around the galactic center. Each star moves along a path determined by the combined gravitational pull of the galaxy's total mass distribution, producing a slow-ordered rotation that unfolds over hundreds of millions of years. Within these neighborhoods, interstellar gas and dust drift through regions of varying density. These materials respond to both gravity and radiation pressure from nearby stars. In some areas, gas clouds remain diffuse and stable, while in others, compression leads to the formation of new stars. The process of star formation emerges where gravity overcomes internal pressure, causing matter to collapse gradually until nuclear fusion begins in a newly formed stellar core. This cycle of collapse and ignition defines much of the visible structure within galaxies. Stars themselves represent stable systems of energy balance, where gravitational collapse is held in check by the outward pressure generated from nuclear fusion. Inside these stars, hydrogen atoms fuse into helium under extreme temperature and pressure, releasing energy that radiates outward into space. This energy maintains the star's structure and produces the light that illuminates surrounding space. The motion of material within and around stars occurs under the influence of intense gravitational and electromagnetic forces, each shaping how matter behaves at different scales. In stellar neighborhoods, velocities remain far below the speed of light under normal conditions. Even the fastest moving objects, such as stellar winds or ejected material from explosive events, do not approach relativistic limits except in extreme cases. These motions are governed by the energy released in stellar processes, which, while immense by human standards, are still constrained by the physical properties of matter and radiation. The region surrounding stars is also filled with charged particles and magnetic fields. These fields guide the motion of plasma, creating structures such as stellar winds and magnetospheres. Charged particles spiral along magnetic field lines, moving in complex patterns that reflect both electromagnetic and gravitational influences. In these environments, motion becomes a combined effect of multiple forces rather than a single simple trajectory. As distance from a star increases, gravitational influence weakens, and particles drift more freely through interstellar space. However, even in these outer regions, motion is not unrestricted. Collisions between particles, interactions with radiation, and residual magnetic fields all contribute to shaping trajectories over time. The environment remains dynamic, with matter continuously exchanged between stars and the surrounding medium. Within this scale, the concept of speed begins to take on a more precise meaning. Velocity is measured relative to local reference frames tied to nearby stars or galactic structures. These frames provide a stable basis for understanding motion, but they also reveal that all movement is still subject to the same underlying physical constraints that apply across the universe. No object within these systems can transition smoothly into the speed of light, because as velocity increases, energy requirements rise sharply. This region also highlights the role of relativistic effects beginning to appear in extreme astrophysical events. Near compact objects or in high-energy stellar explosions, particles can be accelerated to significant fractions of light speed. In these cases, time dilation and energy scaling become relevant, subtly altering the behavior of matter as it approaches extreme velocities. However, even these conditions remain bounded, as no observed process allows matter with mass to reach or exceed the speed of light. Stellar neighborhoods therefore represent a bridge between large-scale galactic structure and the more intense environments where relativistic physics becomes unavoidable. While motion here is still primarily governed by classical gravity and electromagnetism, the first signs of speed-related limitations begin to emerge, especially in high-energy astrophysical processes. As the focus moves inward from these stellar environments, the next layer examines motion within planetary systems, where velocities become more directly comparable to human technology, and where the constraints of approaching light speed begin to appear in more practical and measurable forms. Solar system velocities define the next inward region, where motion becomes directly observable through planetary orbit spacecraft trajectories and the dynamics of small bodies bound to a single star. In this environment, the dominant gravitational influence is the central star, which organizes the motion of planets, asteroids, comets, and dust into stable orbital patterns. Each object moves along a path determined by a balance between gravitational attraction and inertial motion, producing continuous curved trajectories that persist over long timescales. Planets move at speeds that are large in everyday terms, but still extremely small compared with the speed of light. The inner planets orbit more quickly due to stronger gravitational influence from the central star, while outer planets move more slowly along wider paths. These differences in orbital speed reflect the structure of gravitational potential within the system, where distance from the central mass determines the energy required for stable motion. Spacecraft within this region provide direct measurements of how motion behaves under controlled human engineering. Vehicles launched from planetary surfaces must first overcome gravitational binding, requiring large amounts of energy to reach orbital velocity. Once in orbit, they follow predictable paths shaped by the same gravitational laws that govern natural celestial bodies. Even the fastest spacecraft ever built remain far from relativistic speeds, illustrating the enormous gap between human technology and the speed of light. Within the solar system, particles and radiation also move through space, creating a dynamic environment of photons, solar wind, and charged plasma. Photons travel at the universal speed limit, defining a reference against which all other motion is compared. Charged particles from the star stream outward in continuous flows, interacting with planetary magnetic fields and forming complex regions of radiation and plasma dynamics. These particles can reach high energies, but their motion remains governed by electromagnetic forces and does not allow sustained mass-bearing travel at extreme relativistic speeds. Asteroids and comets introduce additional complexity to motion within the solar system. Their trajectories are influenced by gravitational interactions with planets and the central star, leading to long, sometimes chaotic orbital paths. Close encounters between these bodies and planets can significantly alter their motion, but even in such events, their velocities remain within a bounded range determined by gravitational energy within the system. As objects move closer to the central star, gravitational energy increases and orbital speeds rise. However, this increase follows a predictable relationship rather than an unlimited escalation. There is a clear upper range of velocities achievable within stable orbits, and even escape trajectories do not approach relativistic limits. The energy required to accelerate beyond these ranges grows rapidly, reinforcing the separation between everyday astrophysical motion and the extreme regime near the speed of light. In this region, the effects of relativity begin to become relevant in precise measurements. While spacecraft and planets do not reach speeds where time dilation is noticeable in daily experience, scientific instruments can account for small, relativistic corrections in communication signals and orbital calculations. These corrections are necessary for accurate navigation and demonstrate that even within relatively slow-moving systems, the structure of space-time imposes consistent rules on motion. Solar system dynamics also reveal the stability of physical laws across space. The same gravitational principles that govern planetary orbits also apply to distant stars and galaxies, indicating that motion is universally constrained by consistent rules. However, the scale of energy required to significantly alter velocity increases dramatically as objects attempt to approach the speed of light, making such motion unattainable within any natural solar system process. This region highlights the practical boundaries of speed from a physical and engineering perspective. While motion within the solar system is diverse and energetic, it remains firmly within a regime far removed from relativistic extremes. The limitations observed here are not due to technological shortcomings alone, but are rooted in the fundamental relationship between energy, mass, and motion. As attention shifts inward again, the focus moves from large orbital systems to environments where matter interacts more directly with radiation and particles, revealing additional constraints on motion at microscopic scales. Atmosphere and particle environments form the next inward layer, where motion is no longer dominated by large gravitational orbits, but by continuous collisions, radiation exchange, and electromagnetic interactions. In this region, gases surrounding planets are composed of molecules moving at high random speeds, constantly colliding and exchanging energy. Temperature becomes a measure of this microscopic motion, representing the average kinetic energy of particles within the atmosphere. Within a planetary atmosphere, motion is strongly influenced by density. Near the surface, molecules collide, frequently producing friction and resistance to movement. Higher in the atmosphere, where density decreases, particles travel longer distances between collisions, allowing freer motion, but also exposing them more directly to radiation and charged particles from space. This gradient creates layers of differing behavior, each governed by the balance between gravity pulling molecules downward and thermal energy driving them outward. Charged particles introduced into this environment, whether from solar radiation or atmospheric ionization, interact with magnetic fields that surround the planet. These fields guide particle motion along curved paths, producing structures such as auroras and radiation belts. In these regions, motion is not linear but follows spiraling trajectories shaped by electromagnetic forces. Even at high energies, particles remain bound by the rules of field interactions and cannot accelerate indefinitely without losing energy through radiation or collisions. At the microscopic level, particles move according to statistical distributions rather than single deterministic paths. Each molecule in a gas has its own velocity, direction, and energy, but collectively they form predictable patterns described by thermodynamic principles. These patterns remain stable even though individual particles are in constant motion. The average behavior of the system defines pressure, temperature, and density, which in turn influence large-scale atmospheric motion. In upper atmospheric regions, particles can reach higher velocities due to reduced collision rates. Some particles gain enough energy to escape gravitational binding entirely, slowly leaving the atmosphere and entering space. This process, known as atmospheric escape, demonstrates that motion at microscopic scales can overcome planetary gravity when energy exceeds a certain threshold. However, even these escaping particles remain far below relativistic speeds under normal planetary conditions. Radiation within this environment introduces additional complexity. Photons travel freely through the atmosphere, interacting with matter only occasionally. These interactions can transfer energy to particles, increasing their motion or altering chemical structures. Despite these interactions, photons maintain a constant speed, reinforcing the universal limit that governs all massless propagation. In plasma regions of the upper atmosphere, matter exists in a partially ionized state, where electrons are separated from nuclei. Here, motion becomes highly sensitive to electromagnetic fields. Particles accelerate rapidly along field lines, but their paths are continuously altered by magnetic confinement and collisions. Energy input into this system results in increased motion, but also in increased radiation losses, preventing uncontrolled acceleration. Even in these high-energy atmospheric conditions, the relationship between energy and speed remains bounded. As particles gain energy, their velocities approach limits determined by their mass and the structure of space-time. Additional energy input increasingly contributes to relativistic effects rather than proportional increases in speed. This means that pushing particles closer to the speed of light requires disproportionately large amounts of energy, even in environments where collisions are frequent and energetic. Atmospheric motion therefore represents a transition zone between large-scale orbital dynamics and microscopic physical constraints. It demonstrates how energy disperses through matter, how collisions regulate motion, and how electromagnetic forces shape particle trajectories. Although motion here appears highly dynamic and sometimes chaotic, it remains governed by consistent physical laws that prevent unlimited acceleration. As this layer narrows the scale of observation further, the focus moves toward atomic and subatomic structures, where matter itself defines even stricter constraints on motion and energy transfer. Atomic structure and matter form the next inward layer where motion is governed by electromagnetic forces binding electrons to nuclei and by quantum principles that define the stability of matter. In this region, atoms are the fundamental units of ordinary substances composed of a dense nucleus surrounded by a cloud of electrons. The electrons do not orbit in simple paths, but exist in probability distributions that describe where they are most likely to be found. This structure determines how matter interacts, how it absorbs and emits energy, and how it resists compression or disruption. Within atoms, motion occurs at extremely small scales, but remains constrained by the forces that hold the system together. Electrons are bound to nuclei by electromagnetic attraction, and this binding energy defines how tightly matter holds its structure. To change the state of an atom, energy must be added to overcome these binding forces, whether through heating, radiation, or collisions. Even when electrons are excited to higher energy levels, they remain confined within the atom unless sufficient energy is supplied to remove them entirely. At this scale, motion cannot be understood in purely classical terms. Quantum behavior governs how particles exist and interact, meaning that position and momentum are not simultaneously fixed with absolute precision. Instead, particles are described through wave-like properties that define probabilities of location and motion. This fundamentally alters how acceleration and velocity are interpreted, especially when energy is introduced into the system. When atoms absorb energy, their electrons move into higher energy states, or are ejected entirely, producing ionization. Ionized matter behaves differently because charged particles respond strongly to electromagnetic fields. However, even in ionized states, particles remain subject to the same relativistic constraints that apply to all matter. Increasing energy leads to increases in velocity, only up to a point after which additional energy contributes more to relativistic mass effects than to actual speed increase. The nucleus at the center of the atom contains protons and neutrons bound together by the strong nuclear force. This force operates at extremely short ranges, but is powerful enough to overcome the electromagnetic repulsion between positively charged protons. Within the nucleus, motion is highly energetic, but confined with nucleons interacting continuously in a tightly bound system. Despite the intensity of these interactions, the particles remain restricted to sublight speeds due to their mass and the energy structure of the system. Atoms and nuclei form the foundation of all macroscopic matter, meaning that any attempt to accelerate physical objects must contend with these internal structures. As energy is applied to matter, it is distributed across atomic and subatomic systems, affecting electrons, nuclei, and internal binding energies. This distribution limits how efficiently energy can be converted into motion of the entire object. In dense materials, collisions between atoms further regulate motion. When an object moves through matter, it experiences resistance caused by electromagnetic interactions between atomic structures. This resistance converts kinetic energy into heat and internal excitation, reducing the efficiency of acceleration. Even in extremely energetic environments, this conversion process ensures that motion remains bounded by the properties of matter itself, At this level, the concept of speed begins to merge with energy distribution across microscopic systems. Motion is no longer just the movement of a whole object, but the collective behavior of countless interacting particles. Each contributes to the overall dynamics, but none individually can exceed the universal constraints imposed by space-time and mass-energy relationships. As this layer becomes clearer, it reveals that the limitations on reaching extreme speeds are not only due to large-scale cosmic structures or planetary environments, but are deeply embedded within the very building blocks of matter itself. The next inward focus moves into quantum fields and fundamental particles, where these constraints become even more pronounced and universal. Quantum fields and particles form the next inward layer, where matter is no longer viewed as isolated objects, but as excitations within continuous fields that permeate all of space. In this framework, every particle is understood as a localized vibration of an underlying field, and motion is described through changes in energy and momentum within these fields. Space is not empty between particles, but filled with structured fields that define how particles emerge, interact, and transform. Within quantum field, behavior particles are created and annihilated through interactions that follow strict conservation laws. Energy and momentum are preserved in every interaction, meaning that any change in motion must respect these fundamental constraints. As energy is introduced into a system, it does not simply increase speed in a linear way, but redistributes across possible quantum states, including the creation of new particles when sufficient energy is available. At this scale, the concept of a single continuous trajectory becomes less precise. Instead, motion is described through probabilities of interaction and propagation. Particles do not follow fixed paths, but evolve according to wave functions that encode the likelihood of finding them in specific states. Despite this probabilistic nature, measurable outcomes remain consistent and predictable when averaged across many events. Relativity is deeply integrated into quantum field behavior. The structure of spacetime determines how fields propagate and how information moves through them. The speed of light emerges as the maximum rate at which causal influences can travel between regions of space. This limit is not imposed externally, but arises naturally from the symmetry of spacetime itself, ensuring that all massless field excitations propagate at a constant speed. When particles with mass are accelerated, their energy increases in a way that alters their behavior within the field. Instead of allowing unlimited increases in speed, additional energy contributes to changes in momentum that approach an asymptotic limit. This means that as velocity increases further energy, input produces smaller and smaller changes in speed, reflecting the structure of space-time and field interactions. Interactions between particles occur through exchange of field quanta, such as photons for electromagnetic force, or gluons for the strong force. These exchanges transmit energy and momentum across space, but always within the constraint that no information or influence travels faster than light. Even the most energetic processes respect this boundary, preserving causality and the structure of physical law. In high-energy environments, particle collisions can produce new forms of matter and radiation. These events demonstrate how energy can transform into mass and vice versa, but they also reinforce the limitation that no resulting particle can exceed the speed of light. Instead, newly created particles inherit energy distributions that determine their motion within the same universal framework. Quantum fields also explain why attempts to accelerate massive particles require increasingly large amounts of energy as they approach relativistic speeds. The relationship between energy and velocity becomes nonlinear, reflecting the geometry of space-time embedded in the field structure. As a result, pushing particles closer to light speed demands exponentially greater input, while never allowing actual attainment of that limit. This layer reveals that the speed of light is not simply a mechanical barrier, but a fundamental property of how fields and spacetime interact. It defines the structure within which all particles exist and move, ensuring that no physical process can exceed the causal structure of the universe. As this understanding deepens, attention shifts toward the origin of mass and inertia themselves, where the resistance to acceleration becomes a central feature of why reaching light speed remains impossible. Mass and inertia origin form the next inward layer where the resistance of matter to changes in motion becomes a central feature of physical behavior. In this region, inertia is understood as the property that causes objects to resist acceleration when a force is applied. This resistance is not simply a mechanical effect, but is deeply connected to how mass emerges from interactions with fundamental fields. Mass determines how strongly an object responds to applied energy, shaping how motion changes over time. Within modern physical understanding, much of an object's mass arises from interactions between underlying fields, rather than from the simple sum of its internal components. For composite particles such as protons and neutrons, most of their mass is generated by the energy of strong force interactions binding their internal constituents. This means that mass is closely tied to energy stored in dynamic field interactions, rather than being a fixed intrinsic substance. Inertia increases the difficulty of accelerating objects as their energy content grows. When energy is added to a moving object, part of that energy contributes to increasing its velocity, but a growing portion contributes to relativistic effects associated with momentum and energy distribution. As speed increases, the same amount of additional energy produces progressively smaller increases in velocity, reflecting the structure of spacetime and the way mass interacts with motion. At high speeds, the relationship between energy and motion becomes nonlinear. This means that doubling the energy input does not double the speed. Instead, each incremental increase in velocity requires more energy than the previous one. This pattern continues as motion approaches the speed of light, where the required energy grows without bound for any object with non-zero mass. Inertia is also influenced by how particles interact with the Higgs field, which provides a mechanism for mass generation in fundamental particles. As particles move through this field, their interactions give rise to effective mass shaping how they respond to forces. This interaction is uniform throughout space, meaning that inertia is a universal property experienced by all massive particles regardless of location. As energy increases in a moving object, its relativistic momentum grows in a way that reflects both its velocity and its mass-energy relationship. This means that even when an object is subjected to continuous force, its acceleration decreases as it approaches extreme speeds. The behavior is not due to external resistance, but arises from the internal structure of spacetime and field interactions. In practical terms, this explains why no physical object can be continuously accelerated to reach the speed of light. As velocity increases, more and more of the input energy is required simply to maintain the increase in momentum, rather than to produce additional speed. The system becomes increasingly resistant to further acceleration, effectively approaching a limit that cannot be crossed. This layer also highlights how inertia is not an isolated property, but is deeply connected to energy fields and spacetime geometry. The resistance to acceleration is a direct consequence of how mass energy interacts with the structure of the universe, ensuring that motion remains bounded under all conditions. As this inward progression continues, the focus shifts toward the direct effects of relativistic motion itself, where time, space, and energy begin to behave in ways that fundamentally reshape the meaning of speed. Relativistic speed effects define the next inward layer, where the structure of spacetime itself begins to reshape how motion, time, and distance are experienced. In this region, the laws of motion remain consistent, but their consequences change as velocities become a significant fraction of the speed of light. Space and time are no longer independent backgrounds, but are joined into a single interconnected structure where measurements of distance and duration depend on relative motion. As an object accelerates to higher speeds, time for that object begins to pass differently compared with a stationary observer. This effect, known as time dilation, means that moving systems experience time more slowly relative to external reference frames. This slowing is not subjective but measurable, confirmed through observations of fast-moving particles and precise timing systems. The closer an object's speed approaches the speed of light, the more pronounced this difference becomes. At the same time, lengths measured in the direction of the motion contract relative to external observers. This length contraction reduces the effective distance an object experiences as it moves at high speed, altering how space is perceived in different reference frames. These effects together ensure that the speed of light remains constant for all observers, regardless of their relative motion. Energy requirements also change dramatically in this regime. As velocity increases, additional energy contributes less to acceleration and more to changes in relativistic momentum. The relationship between energy and speed becomes increasingly steep, meaning that even small increases in velocity near the upper limit require enormous amounts of energy. This behavior reflects the geometric structure of space-time, where the speed of light acts as a boundary that cannot be reached by objects with mass. The relativistic combination of velocities ensures that no matter how speeds are added together in different reference frames, the result never exceeds the speed of light. This rule preserves causality, ensuring that cause and effect remain consistent across all observers. It also prevents paradoxes that would arise if information or matter could travel faster than light. Particles accelerated in high-energy environments provide direct evidence of these effects. In particle accelerators, massive particles can be pushed to extremely high speeds, yet as they approach the speed of light, they require exponentially more energy for smaller increments in velocity. Despite continuous energy input, they never reach or exceed the limit, instead approaching it asymptotically. Radiation emitted by accelerating charged particles also changes under relativistic conditions. As speeds increase, emission patterns shift and energy losses become more significant, adding further constraints on how efficiently acceleration can proceed. These effects reinforce the idea that motion at extreme speeds is not only difficult, but fundamentally constrained by the structure of space-time. Relativistic motion also alters the relationship between mass and energy. As velocity increases, the energy of a moving object increases significantly, reflecting its growing relativistic momentum. This does not mean that mass itself changes in a simple way, but rather that the energy required to continue accelerating becomes increasingly large, reinforcing the asymptotic nature of the speed limit. Within this layer, it becomes clear that the speed of light is not merely a threshold, but a structural feature of space-time. It defines how space and time transform between observers and ensures that all physical laws remain consistent across different frames of motion. No amount of energy or sustained acceleration can alter this structure, only approach it more closely. As these relativistic effects accumulate, they lead directly into the next layer, where the practical limits of energy input become the dominant reason why reaching the speed of light remains physically impossible. Energy requirements explosion forms the next inward layer, where the practical limits of acceleration become dominated by the rapidly increasing energy needed to approach the speed of light. In this region, motion is still governed by the same relativistic laws, but the focus shifts to how energy must be supplied and distributed to sustain further increases in velocity. The relationship between energy and speed becomes increasingly extreme, creating a situation where each additional increment of velocity demands disproportionately greater input. As an object moves faster, its kinetic energy rises in a nonlinear way. At low speeds, increases in energy produce noticeable changes in velocity, but as speed grows closer to the speed of light, this relationship changes dramatically. Most additional energy contributes not to increasing speed, but to relativistic momentum and energy within the system. This shift means that acceleration becomes progressively less efficient, even when large amounts of energy are supplied continuously. In practical terms, this creates a steep energy barrier. To move from already high speeds to even higher ones requires vastly more energy than moving at lower speeds. As velocity approaches the speed of light, the energy required grows, without bound meaning it trends toward infinity for any object with mass. This does not occur abruptly, but as a smooth and continuous divergence reflecting the underlying structure of spacetime. This energy divergence is not a failure of engineering, but a direct consequence of relativistic geometry. Spacetime itself enforces the relationship between energy and velocity, ensuring that the speed of light remains an unattainable limit for massive objects. No known physical process can bypass this requirement, because it is embedded in the fundamental equations that govern motion and energy conservation. In high-energy environments such as particle accelerators or astrophysical jets, this energy barrier becomes directly observable. Particles can be accelerated to extremely high fractions of the speed of light, but each additional increase in velocity requires exponentially more energy input. Even with advanced technology, the acceleration curve flattens, showing a clear asymptotic approach toward the limit without ever reaching it. Energy losses also increase significantly in these regimes. As charged particles accelerate, they emit radiation which carries away part of the input energy. This radiation loss becomes more pronounced at higher speeds, further reducing the efficiency of acceleration. The combination of increasing energy requirements and energy loss mechanisms creates a natural ceiling on achievable velocities. The structure of matter itself also contributes to this limitation. As energy is added to a system, it can be redistributed internally, increasing thermal motion radiation emission or particle production, rather than contributing directly to bulk motion. This internal distribution of energy further reduces the fraction of input energy that translates into forward velocity. Even hypothetical systems with perfect energy efficiency would still face the relativistic divergence of required energy near the speed of light. This means that the limitation is not technological, but fundamental. It arises from the geometry of spacetime and the invariant speed that defines causal structure in the universe. As this energy barrier becomes clearer, it reveals why the speed of light is not simply difficult to reach, but fundamentally unreachable. No finite amount of energy can complete the final step to that limit, because the required energy grows beyond any bound as velocity approaches it. This understanding naturally leads into the next layer, where the role of causality and information flow further reinforces why motion itself cannot exceed this universal constraint. Information and causality form the next inward layer, where the limit on motion becomes tied not only to energy and mass, but to the structure of cause and effect itself. In this region, physical processes are understood as chains of events, where one interaction leads to another through the transfer of energy and information. These transfers occur across space-time in a way that preserves a consistent ordering of events, ensuring that causes always precede their effects within any valid reference frame. The speed of light emerges as the maximum rate at which information can travel between separated regions of space. This limit ensures that no signal influence or physical interaction can propagate instantaneously or exceed this universal boundary. It is not simply a limit on objects moving through space, but a constraint on how space-time itself transmits changes from one location to another. When events occur in different locations, their ordering can appear different depending on the observer's motion. but causality remains preserved because no information can travel faster than light. This means that all observers agree on cause and effect relationships even if they disagree on timing. The structure of space-time is arranged so that causal connections remain consistent under all transformations of motion. If faster-than-light travel were possible, it would allow situations where effects could precede their causes in some reference frames. This would break the logical structure of physical law, making it impossible to define consistent sequences of events. The absence of such behavior in all observations indicates that space-time enforces a strict causal order through its geometry. In physical interactions, forces are transmitted through fields that propagate at finite speeds. Electromagnetic interactions, for example, are carried by photons which always move at the speed of light in vacuum. Gravitational effects, as described in modern physics, also propagate at finite speed, ensuring that changes in mass distribution influence distant regions only after a delay consistent with light speed transmission. These delays are essential for maintaining causal consistency. At high energies, particles can be accelerated to extreme velocities, but the transmission of forces that accelerate them still obeys the same causal limits. No matter how intense the interaction, the influence spreads through space at or below the speed of light. This ensures that even in the most energetic environments, causality remains intact and no instantaneous effect occurs across distance. Information itself is physical in this framework, meaning that it cannot be separated from energy and matter. Any attempt to transmit information requires the movement of physical carriers, whether particles, fields, or waves. These carriers are bound by the same relativistic constraints as all other forms of motion, reinforcing the universal nature of the speed limit. As velocity increases toward the speed of light, the ability to exchange information between different regions of a moving system becomes increasingly constrained. Communication delays grow, synchronization becomes more difficult, and internal coherence across systems begins to break down if relativistic effects are not accounted for. This reflects the deep connection between motion and the structure of information flow. The impossibility of exceeding the speed of light is therefore not only a statement about energy or inertia, but also about the preservation of logical structure in the universe. Causality depends on a consistent ordering of events, and this ordering is enforced by the same limit that governs the propagation of light and all other massless interactions. This layer shows that motion is inseparable from information transfer, and that the speed of light defines the boundary within which all meaningful physical relationships are maintained. As this becomes clearer, the focus shifts toward experimental evidence from particle physics where these principles are directly observed under controlled conditions. Particle acceleration limits form the next inward layer, where theoretical constraints become directly observable through controlled experiments involving high-energy particles. In this region, motion is studied by accelerating subatomic particles using electromagnetic fields and measuring how their energy and velocity change under extreme conditions. These experiments provide some of the most precise confirmations of relativistic physics and the universal speed limit. In particle accelerators, charged particles are guided along circular or linear paths using powerful magnetic and electric fields. As energy is supplied, the particles gain momentum and their speed increases. However, as their velocity approaches the speed of light, the relationship between energy input and speed change begins to shift dramatically. Additional energy contributes less to increasing velocity and more to increasing relativistic energy, consistent with the structure of space-time. Despite continuous acceleration, particles never reach the speed of light. Instead, they approach it asymptotically, getting closer and closer without ever crossing the boundary. This behavior is not due to mechanical limitations in the accelerator, but arises from the fundamental equations governing motion at high energies. The observed trajectories match theoretical predictions with extremely high precision, confirming that the speed of light acts as an absolute limit for particles with mass. Synchrotron radiation becomes increasingly important in these systems. When charged particles are forced to change direction at high speeds, they emit radiation that carries away energy. This energy loss becomes more significant as velocity increases, requiring even greater input energy to maintain acceleration. In circular accelerators, this effect places practical constraints on how far particles can be pushed toward the speed of light, especially for lighter particles such as electrons. Linear accelerators reduce some of these losses by allowing particles to travel in straight paths, but even in these systems the relativistic energy barrier remains. No matter how efficiently energy is supplied, the asymptotic nature of relativistic motion prevents particles from ever reaching or exceeding the speed of light. Each incremental gain in velocity requires a disproportionately larger energy input consistent across all experimental setups. Experimental observations also confirm time dilation effects in fast-moving particles. Unstable particles created in high-energy collisions live longer when moving at speeds close to that of light, as measured in laboratory frames. This extended lifetime matches predictions from relativistic physics and provides further evidence that time and motion are deeply interconnected at high velocities. Particle collisions also demonstrate how energy transforms into new forms of matter. When particles collide at extreme energies, new particles can be created distributed according to conservation laws. These processes show that energy is not simply converted into motion, but into a range of physical outcomes governed by quantum field interactions. Even in these high-energy events, no resulting particle exceeds the speed of light. The consistency of these results across different experiments and facilities confirms that the speed limit is not an artifact of specific conditions, but a universal feature of nature. Every measurement aligns with the same underlying structure, where energy, momentum, and spacetime geometry together enforce a strict upper bound on velocity. These experimental findings provide some of the strongest empirical support for relativistic physics, showing that even under the most extreme controlled conditions, matter cannot reach the speed of light. As this layer concludes, attention shifts toward the fundamental constants of nature that encode this limit directly into the structure of physical law. Fundamental physical constants form the next inward layer where the deepest constraints on motion are encoded directly into the structure of physical law. In this region, the behavior of the universe is not only described by relationships between energy, mass, and space-time, but also defined by fixed numerical values that remain constant across all known conditions. Among these constants, the speed of light in vacuum stands as a central limit that shapes how all other physical processes unfold. The speed of light is not simply a measured quantity, but a defining feature of spacetime itself. It determines how distances and times are related, how fields propagate, and how causality is structured. Because this constant is invariant for all observers, it provides a universal reference point for all motion. No matter the state of motion of an observer, light is always measured to travel at the same speed, reinforcing its role as a fundamental boundary. Other constants of nature interact with this limit to shape the behavior of matter and energy. The gravitational constant determines the strength of attraction between masses, influencing the structure of stars, planets, and galaxies. The Planck constant governs quantum behavior, setting the scale at which energy and matter exhibit wave-like properties. The elementary charge defines the strength of electromagnetic interactions, controlling how atoms and molecules form and interact. Together, these constants establish the framework within which all physical processes occur. Within this framework, the speed of light emerges as the conversion factor between space and time. It links spatial distances with temporal intervals, ensuring that changes in one cannot be separated from the other. This relationship forms the basis of relativistic spacetime, where motion is described not only in terms of distance travelled, but also in terms of how time is experienced along different paths. Because these constants are fixed, they impose strict limits on how energy can be converted into motion. No adjustment of physical conditions can alter the invariant nature of the speed of light. This means that all attempts to accelerate matter must operate within a framework where the upper limit on velocity is already built into the structure of the universe. The consistency of these constants across observations reinforces their fundamental nature. Measurements conducted in distant regions of space and at different times in cosmic history show the same values within extremely precise limits. This uniformity indicates that the laws governing motion are not local or temporary but universal and stable across all known scales. In theoretical physics, attempts to describe motion at extreme energies always incorporate these constants from the beginning. Relativistic equations naturally include the speed of light as a limiting factor, ensuring that predictions remain consistent with observed behavior. Any deviation from these constants would produce measurable contradictions in particle behavior, orbital dynamics, and electromagnetic interactions, none of which are observed. The presence of these constants also ensures that spacetime has a consistent structure that does not allow arbitrary distortion of causal relationships. The speed of light in particular preserves the ordering of events and ensures that physical interactions remain predictable across all frames of reference. This stability is essential for the coherence of physical law. As this layer becomes clear, it shows that the limitation on reaching the speed of light is not an isolated rule, but part of a deeply interconnected system of constants that define the universe itself. These constants collectively determine how motion, energy, and information behave at every scale. This understanding leads into the final layer where all previous constraints converge into a single conclusion about why reaching the speed of light is fundamentally impossible for any object with mass. Absolute speed barrier forms the final inward layer, where all previously described constraints converge into a single unified limitation on motion. In this region, the behavior of matter, energy, space-time, and information is no longer considered separately, but as parts of one coherent structure that defines what motion can and cannot achieve. The speed of light emerges not as a threshold that objects approach by chance, but as an intrinsic boundary embedded in the geometry of the universe. For any object with mass, motion through space requires energy, and that energy is always distributed between increasing velocity and altering the relativistic structure of momentum. As velocity rises, the proportion of energy needed to produce further increases in speed grows rapidly, while the portion contributing to actual acceleration shrinks. This relationship ensures that the closer an object gets to the speed of light, the more resistant its motion becomes to change, regardless of how energy is applied. The asymptotic nature of this limit means that reaching the speed of light would require infinite energy. No physical system can supply an infinite amount of energy in a finite region of space-time, and no process can bypass this requirement without violating the established structure of physical law. This is not a technological limitation, but a consequence of how space-time defines motion for all massive objects. At the same time, causality reinforces this boundary. The speed of light defines the maximum rate at which information and influence can travel, ensuring that cause and effect remain consistent across all reference frames. If massive objects could reach or exceed this speed, the structure of causality would break down, leading to contradictions in the ordering of events. The absence of such contradictions in all observed phenomena confirms the universality of this constraint. Every experimental result in particle physics, astrophysics, and cosmology aligns with this framework. Particles accelerated in laboratories approach, but never reach the speed of light. High-energy cosmic particles observed in space behave according to the same rules. Light itself always propagates at this constant speed regardless of the motion of its source or observer reinforcing its role as a fundamental feature of spacetime rather than a contingent property. The origin of this barrier lies in the deep relationship between space and time. In relativistic spacetime, motion is not simply movement through space, but a combined trajectory through both space and time. As velocity increases, the direction of this trajectory shifts in such a way that further increases in spatial speed become increasingly constrained. This geometric structure ensures that the speed of light remains an unreachable boundary for all matter with mass. No known physical mechanism allows this structure to be altered. All interactions, whether gravitational, electromagnetic, or nuclear, operate within the same spacetime framework. Even extreme conditions, such as those near black holes or in high-energy particle collisions, do not modify the fundamental limit. They only demonstrate its effects more clearly. In every case, the same asymptotic approach is observed. The impossibility of reaching the speed of light is therefore not an external rule imposed on the universe, but a reflection of its internal consistency. It arises from the way energy, mass, and spacetime are fundamentally connected, ensuring that motion remains bounded and causally coherent across all scales. Within this final layer, all earlier regions converge into a single realization. The structure of the universe itself defines the limits of motion. No path exists that leads beyond the speed of light, because every possible path is shaped by the same underlying geometry that enforces the limit. The narrative of motion from the largest cosmic scales down to the smallest quantum interactions consistently returns to this boundary. It is present in the expansion of space, in the structure of galaxies, in the behavior of atoms, in the dynamics of particles, and in the flow of information itself. Across all levels, the same constraint remains unchanged. In the end, the reason humans will never reach the speed of light is not due to engineering difficulty or lack of progress, but because motion itself is defined in a way that makes such a journey impossible. The limit is not ahead to be reached, but built into every step of movement from the very beginning.